ANSYS Simulation, Lecture 8, Part 1, Steady-State Thermal Analysis. It's a heat sinks problem. And load ANSYS software and enter ANSYS Workbench. And the first page will be project schematic, which is the organizing interface of ANSYS. And in these procedures, the red color icons will be thermal analysis procedures, and the green color is solid mechanics procedures. Blue color is fluid dynamics procedures, and the brown color is electromagnetic procedures. And for thermal analysis, there are two procedures. The first one is steady-state thermal analysis, and the second is transient thermal analysis. So we'll implement steady-state thermal analysis and drag drop on geometry. And I'll edit the material and enter data source, general material, and I'll add aluminum alloy for the procedure, and enter ANSYS mechanical by editing the model. And now we are in ANSYS mechanical environment. Since this is a steady-state thermal analysis, so initial temperature is not that important, but we'll still enter the initial temperature, and I'll make it 25 degrees C. And first of all, I'll link the geometry with the material. So I choose material aluminum alloy for the product, and the heatsink geometry step 1, the material step 2. For the step 3, I will update the mesh. For step 4, since I have already entered the initial temperature of the body, and then I'll enter the heat source, which is heat flow, on the bottom surface of the heat sink. And the heat source will be 28 watt to simulate the heat generation of CPU and the heat is emitted to the bottom surface of the heatsink. And this is the loading. For boundary conditions, I will choose convection heat transfer and apply on all surfaces except for the bottom surface, where I'll choose all surfaces. All surfaces. And deselect by Control key, deselect the bottom surface. Apply. So there are 156 surfaces that are in contact with the air. And make sure the unit is right, because the unit is metric unit. If you choose the millimeter of length, the value will be different. So make sure that you use SI unit and enter 10 as the coefficient of convection for the stagnant air. And the ambient temperature, or the room temperature, will be 25 degrees C. And here the most important thing is that this value is for the stagnant air, the convection heat transfer coefficient of the stagnant air. For a fanned environment, the value will be as high as 30. So this is a stagnant air condition for a air-cooled heat sink. So this is the convection heat sink, and this is the heat source. So I finished with the fourth step, the loading and boundary conditions. So for the result, I will choose temperature and then run the procedure, and then I'll probe the center of here. So at this spot the temperature will be 120 degrees C, and this is the temperature of the heat sink where the system get thermal equilibrium, become very stable. So it is a temperature where the system become homogeneous or thermally equilibrium. So this is how a steady-state thermal analysis is implemented. In the next part of this lecture, we'll talk about transient thermal analysis, where the temperature will rise from 25 degrees to 120 degrees. So we'll compare both cases to let you know that a steady-state thermal analysis is actually the stable state of transient thermal analysis.